Hey guys, this is Eric Weingarten with Weingarten Racing. This should be put out on Sunday, and usually Sunday I do heavy tech videos. This Sunday I'm not. I'm going to start off with just talking about some of the comments about these heads from my previous video. If you haven't watched that one, it was put out on Wednesday. It was comparing two heads that flow close to the same, and these are the two heads. There were several comments, and I'm going to start the video by going over the comments that some people had left. And then what I'm going to do is I'm going to splice in an old video but talking about overlap flow. The other video was really long and I don't know that people got to see it, so I'm just going to put it in there and try to make this video somewhat shorter. I know you would like to have me do a different in-depth tech video on this Sunday, but it is Labor Day weekend. I still have to smoke a Boston butt, and there's a lot of stuff I still have to get done in the shop here because we don't take days off here in the shop. At least I don't. So it's every day I have to work. I'm that far behind. But anyway, let's get to it. Just a recap of what the video was, just to help some of you guys that haven't seen it. What I did was I compared the flow on these two heads, even though they're vastly different. So I'll talk about the heads real quick, and I mean really quick. This first one is a small block Chevy Headhunter head that I have ported. It's not how it came from the factory. It is still a 23-degree valve angle. It's got 40-60 valve spacing. The intake valve size was 215, exhaust valve size 1.6. When you measure the distance, it's 5.5 inches long, the length of the runner. It came in, I did CC this one at 235 cc's, which gives an average cross-sectional area of 2.61. This is my Brodix Dragon Slayer. It's the 255 standard wing, so it's got a little wing thing in it, and I'll just so you can see, there it is. Anyway, this one is standard valve spacing, standard height, it's not raised runner. 255 cc's, it's a shorter runner than the Headhunter. It's a 23-degree one too. It's standard valve spacing though, so that is different. It's got a 214 intake valve compared to a 215 from this one. The exhaust valve is 1560. Now, I flowed, this one by the way comes out with an average CSA of 2.88. The pinch on this one by the way is 2.81 or 2.82. This one comes in at 2.3, much smaller. The reason for that is because of the oval design, so it takes up area. This is kind of weird, but the width on this is the same width on that. This one's taller than that, and of course, since it has less radius in the corner, there's more area. Now, when I flowed them, though, these are the results from the Superflow bench. This is what they did, the Headhunter did. If you look at peak flow, it's 351. And if I look at 400, 252, and at 600, 320. Compare this to this one. This one is peak flow is 353, so it's really close to the same. The 400 number is 265, much better. 600 number is 332. Okay, so there's your recap of it, but here's the comments. Someone said, other people have said, you need to do more work on this because the air velocities in this port is extremely fast. Because think about it. It's moving almost the same air as this one, but the port size itself smaller. So that means the air speeds are quicker. Now, several people, well, I shouldn't say several, but some people commented, you need to do more work on this. I'm going to tell you why I don't, and there's a reason for it. And then this head, if you look at its velocity, I did measure the velocities. If you watch the last video, you can see it. Through the pinch, this one was 320. This one's extremely fast at 380. Now, I will say this, which I didn't say in the last video, but I want to give you some information. Port shapes can determine how much airspeed a port can maintain. Now, that seems a little confusing, but what I'm saying is a square design like this or a poor port shape, usually you have to have a slower airspeed so that it doesn't separate on the short side or different things overall. A better port shape can maintain a higher velocity through the port without the port becoming unstable, okay? So in other words, if your port shape's good and the design's better, it can maintain a higher speed without it losing flow as the valve increases or stability. On a poor shape, you have to slow the air down so that it doesn't become unstable. So that's one thing I want to address. This head is perfect for what I'm going to use it for. This is for customers and it's perfect for what he's doing it for. Now let me explain. This is going on a 406. So but it's only going to make, I really wanted to make power between 63 and 6,500 RPM. Now it does going to have a torque storm supercharger, but it's going to make a max of maybe 7 pounds of boost, maybe 10 if I'm lucky, but most likely it's between 5 and 7. The goal for the engine is only to make 800 horsepower with the torque storm. That's it. I don't really care if it makes more. You might say, why? Well, the torque storm itself is only rated at 770 CFM. So if I have a big runner such as this, that blower is only going to spin so much to fill in that runner. It doesn't have enough volume to fill in a bigger runner. So in that case, this blower is spinning harder. It's not putting out any more boost. It's really not going to need more power. But regardless, this head is made for smaller RPM, which is what I want the engine to be. And this is going in the S10. It already has an engine that spins 7,500 RPM. This one is perfect for what it will be. Now, I know you're like, well, the air speeds are fast. If you had boost, wouldn't the air speeds increase? You're correct. What will end up happening is it will take that velocity map that you looked at and will fill in more of the areas become faster. This shape, from the flow bench experience that it's showing, will be able to maintain it because it's not spinning a lot of RPMs. What can happen with blowers, and I haven't really gone over this, but new to you, the blower itself will cram more air through there, all right? It's going to cram more air through there, increase the air speeds. It's still going to push it through. And it's going to keep doing that, and it's still going to keep making more power until it takes more effort to push the air through than the power that the engine's making. So hopefully that makes some sense to you. So the blower is going to keep going. Once it becomes more of a restriction, you can try to add more boost, and you will make no more power because the amount of power it takes to make the more boost, because the port's too small, cancels out any power you made by shoving more air through it. That's what's going to happen. And I see these, by the way, in several people that have like turbo situations. And they're like, well, I went from, let's say, 15 pounds to 20 pounds of boost, and it didn't make any more power. It's kind of leveled off. Well, what really happened is it took more energy to get the air through than what you made from the extra boost. And it happens. This one's really a low boost situation, so it's probably not going to be an issue at all. Now, that's what this is designed for. This one designed for a bigger engine, a 434, and it's going to make peak power at 7,000 RPM. So because of that, the port size itself is bigger. Because it has a bigger engine it has to support, it's turning more RPM. And it is not going to have a power adder. Now, going to this head is perfect for what it's going on. You know, low RPM deal, which I know is like 6,500 seems like a lot. It's not to me. Lower RPM deal. For the most part, it will never be there except for at the track. I'm probably going to shift to maybe 65 and it drops down to 62. I'm cool with that. It's going to work great for that. This one's going to work great for what he's doing. And this is kind of what I want to make a point with the video. You can have a head that's great for one engine, but will be completely a turd for the other. Because let's say I swap these. Let's say I took this head, because they flow the same or close to it. Took this head and I put it on the engine that it's going on. Here's what's going to happen. This thing is going to be a turd compared to this down low. So what I mean by this is, if I'm driving this, driving experience with this one will be far worse than that, because this one's going to have more torque coming off the whole way as I'm driving it than this head. In race form, this one's still probably going to be faster because it's not turning enough RPM for these to really get the advantage. So I'll have to spin the supercharger faster to get the same amount of boost, but it may run the same. Well, I doubt it. I just don't think this one's going to make the power of this one, because that supercharger will not. Now, if I had a Pro Charger, like a bigger Pro Charger that I can spin higher, this will probably do it, because then I can maintain the same amount of boost as that head, and this one will go faster. But I don't have that. I just wanted to use a torque storm. I like the lifetime warranty. Pro Chargers, there's plenty of people that have experiences with Pro Chargers breaking. I just didn't want that. Lifetime warranty with torque storm. It's just really a street truck. It's not really a race truck, even though it'll be raced. You get the idea. But anyway, let's take the head and let's say I reversed this, and I gave this head my great for what I'm doing, and I put it on this guy's 434. Here's what he's going to experience. He's going to have an absolute torque monster all the way to about maybe 55, 56, maybe pushing 6,000. At that point, it's going to feel like it's not pulling anymore, because it won't. The air speeds are too fast. He doesn't have a blower to shove more air through, And what's going to happen is it's called pumping losses. It's going to take more energy to push the air or suck the air in through this than it can maintain. It's going to not make any more power. So if you were to graph these and you look at this versus this, probably up to about 55, maybe 5,200, this head's going to be much better than this one. It's going to make more torque and everything else. From that point on, this one's going to dominate. We're talking like at 52, they're probably the same. But by 7,000, this one's probably going to be 30 to 40 horsepower more than that one would be, even though they flow close to the same, because this one's targeted for a different engine than this one. So this one I put on here, my engine becomes a turd. This one I put on here, absolute torque monster, then a turd. The point I'm trying to make is heads are sized for the specific application that they're going on. You can't just look at flow numbers because these are the same. This one's great for what it's going on, great for what it's going on. Flow numbers only give you part of the picture. The size is really what is important per the engine. And that's why you can have someone who buys a great set of heads, puts it on a wrong application, and makes a turd. So anyway, hopefully that answers some of those questions for that. I'm gonna go ahead and tag on an overlap video. I do appreciate you guys, for everybody that's been watching through this, and you guys have a great Labor Day. I gotta get to grinding. So I'm gonna tag on the overlap video and you guys enjoy. Okay, one more thing. I don't mind if you guys put your 2 cents in on whatever I'm describing in a video, but don't put in your 2 cents if you ain't got change to spare, if you know what I mean. Anyway, this is the next manifold to get ready to port. Here comes the overlap video after this. Okay, this may take a minute to explain. I'm just using it as a loose term, but to explain this, but I'll do my best. And bear with me as I try to explain this because this is a more complex term. So here's what we have. We have our valve set up in like an inline head. Now these could be reversed, intake or exhaust, doesn't matter. But anyway, when crossflow happens is during the overlap period of the cam, and that's actually the most important point in an NA engine, because what happens during overlap, you have the exhaust valves open and the intake valve are open at the same time. And the reason why this is important is because the first draw or pull on the intake port itself comes from the exhaust gases leaving the cylinder. That creates a pull or a vacuum that starts pulling from the cylinder that eventually pulls from the intake, because they're both open at the same time. Now, getting that right is the responsibility of the cam, but there are things that cylinder heads can do that kind of help it. And one of those things I call, and I think others would call it too, is crossflow. And that's the air that goes around and towards the exhaust valve. There's a certain amount of crossflow that we need. The more helps out to an extent, and we'll get to that in a minute. So if you look at an inline head like this case, what would happen is when the exhaust valve's opened and it starts to pull or it starts letting out the exhaust and it's about the end of its cycle and it starts to create a vacuum or a draw inside the cylinder, the intake valve comes open. Now, the air itself, if you think about it, my port's going to be pointing this way because you can look right here, it's between the two. The air is going to go this way, it's going to hit the cylinder before it can get here. In other words, this exhaust valve has to act on all this area before it can actually get to this. I know you think, well, what doesn't it act here? It does, but if you think about the airflow itself, you're going 90 degrees in and that way. So it's much harder for it to get the crossflow during the overlap period. And before someone says, well, you don't want all the air coming in and going out the exhaust valve, that's ridiculous. Well, that's the duty of the cam timing itself, to get those points right where it's not taking so much in that it's going out the exhaust port. We want it to start trapping in there. But this is a typical inline head. Now, this seems great, but if you notice, our chambers usually come up and come down just to aim it at this so it can draw more there. Now, if you look at the SB2 head and splayed heads, they're aiming in the big block head itself. The valve arrangement is different. It's not in line like this. So what they do is they move the intake something like that, and they move the exhaust something like this. Now, this helps out crossflow. And what I'm talking about is, now if you look at it, so our intake port's here between these two bolt holes. Now, it's not going to go 90 degrees to get the exhaust valve. It's going right there, which if you think about it, my cylinder is actually spinning that way. Now, big blocks, by the way, are something like this. SB2s might be a little bit more. And then you start getting to the really cool stuff that's something like this. And we'll get to Hemis in a minute because someone's about to mention, I'm sure. But anyway, the reason why these make more power is because not only is the valve arrangement, you got your intake port coming here leading right towards that, you also have, most of those heads have a cant where the valve's not just tilted this way, because most heads are tilted this way anyway, but they also have a tilt this way. So it's opening, the valve's opening away from the bore the whole time, not just this way, but also this way, getting out of the way of this bore line, getting more flow. You get the idea. The exhaust valve's doing a similar thing in the same point, and it helps the flow across. So in other words, more air is getting in during the overlap before the piston starts coming in to draw more. If more air gets in, more power. That's typically why the design of a head that's something like this gives you a better chance to make more power. Now, it doesn't mean it's going to make more power, but the design is there to help it make more power. Now, someone's about to say, well, what about a Hemi? Because if you look at a Hemi, the bolts would be here and here to take out this middle one, or maybe there is one, depending on how they do it. The air comes in, and guess what? It goes straight out, straight to the exhaust, which seems like it'd be great, except for NA, it's too much. It's what ends up happening is it's got such an easy draw, it actually literally does pull the intake air charge out the exhaust, and becomes kind of an issue. But it's beneficial for power adder, because if you think about it, I'm pulling more air in and out. So I built already a bunch of cylinder pressure. It's easier for that exhaust to get out and this to bring more in. Hemis typically make more power boosted or power adder deals because their crossflow is too much for NA, perfect for the power adder deal because it's easy to get the stuff out. It's much easier. So anyway, NA, it takes too much of it away unless if it's in here than out there. Because if you think about it, they're not, by the way, Hemis are not straight up and down. You have a valve that's literally like this. And the intake valve's or exhaust valve's literally like this. It's just whoop, you get the idea. So anyway, back to the SB2 thing. SB2s should make more power because it's got more that it could trap during overlap period. But beyond that, you've also got some other things that should make it better than a wedge head. Some wedge heads is the ports are higher. It's got a smaller angle valve, degree of valve. It should make more power. Now, saying that, in my shop, I have seen two, and they've flowed 400 CFM, but I've seen wedge heads, like my 13 degrees, flow 422, so they've flowed more than even those. But that's kind of where the flow bench might lead you astray, because for getting the flow, the SB2 still would trap more air during the overlap period than a wedge head would, even though they flowed the same on the bench. And that gives it more, you can have two that flow the same, and that one will make more power because of it. So that's something. But I want to show you something cool I was really hoping to put together and didn't quite, because I want to show you this. This to me is neat, and it's a project I've been trying to get accomplished. Maybe you guys can help if you know a CNC machinist, because it'd be great. This next part's kind of weird, but it relates to this. All right, let me take you over here. Let me show you what this is. This is a piston in a hole, and you're like, big deal. This is a cylinder sleeve, and I'm gonna show you how our flow benches work. We have a cylinder, this is from Brzezinski. Some people have these clear acrylic ones. I don't know how they exactly, unless you're a genius or got it exactly figured out, but the Brzezinski is all CNC worked, and it locates the cylinders directly where they would be, where the head would sit directly as it should on the engine block, so that you're able to simulate the actual where the head would be in relation to the cylinder for the head. But anyway, Brzezinski has this thing called the slider. That's this top plate. And then it's got this bore, and they make different bore sizes. And this right here is the flow stand. By the way, this thing costs a fortune. Anyway, this is a bore sleeve. Okay, and what I did was I put a piston in it. And I put a stop underneath it so I could set the height of the piston. And what I plan to do, and this hasn't got accomplished yet, was this whole setup right here would be on the stand, and I'd have it just sitting like right here. All right, and then I would have a slider that sits on top of that, like it should be, just like it's sitting now. So you could picture this with a piston inside, head on top, and I'd have the valves actuated. And then what I was gonna do was on the head itself, the exhaust port, I was gonna have a hose that went to here, this flow bench. And then on the intake port, I was gonna have a hose that went to this bench. And so you have the head sitting up here with the valves here, and one going to one bench, one going to the other bench. I'm like, why would you do that? I was gonna simulate overlap flow. Because if you notice, this is a dome piston. And the dome piston, I was gonna try to get it at a height that it would be when the valves open and kind of see what happens during overlap as far as flow. Because one major disadvantage to a flow bench of many is when I look, do you see a piston in there? No, but you know what every engine has? A piston. So as I'm measuring flow, because this is the only way you could do it, is the flow is drawing directly down. So, but if you look during overlap flow, which I just described, the air is actually being pulled from the exhaust port. So if I was able to create a suction, I could actually open the two valves and see the air going around for like cross flow. I'd be able to actually measure that. And I would see from this bench how much intake air is going. On that one, how much exhaust air was moving. And I could see how that was actually happening during overlap. And here's something beneficial even more. You could see if the piston itself affected flow. Because I don't know of any other way right now to see how the piston affects flow. We just assume it does. So like here we have a nice piston. It gets a dome, obviously, and it takes up the chamber. Well, what if this design changed everything you did on the port? What if it made things flow so much worse? So I wanted to see an exact actual representation of how it'd be, or at least as close as I could be. Because in all fairness, the two valves are only open during overlap when the piston's pretty close to the top, which also would be when the dome would affect it the most. Because as the intake valves open more, guess what? The piston's further down on the bore. It probably plays a less important part of what's going on as far as flow-wise goes, but it would reveal all this. At least that's what I was hoping. Then maybe I could do wet flow and I could see how the domes were affecting everything and see what's going on, or even if these valve notches played a part. There was a bunch of different things to test. I guess if the Engine Masters Challenge was still going on, I probably would have ever tested this, but as it is, it was just something for fun. Because then I could set the piston at different heights, try different pistons, maybe model my own piston. Just get the notches, blend them how I maybe wanted, design a dome that would to make the right compression ratio. You could grind till you figured out this is the best flowing dome I've got. Instead of like it is, where most of them just like, here's our chamber, we digitize it, it's gonna go be, it looks like it's gonna fill up the whole chamber, there's your spark plug, and bada bam. But you would have a better idea is what I'm trying to say. And I don't think I'm the only one that's ever thought of this. I know some other people probably have. Anytime you have a great idea, I promise you 5 other people have already thought of it. Anyway, what I needed to make this happen, which hasn't yet, I needed to make a plate that would attach to this bench, and then another plate that would attach to the exhaust port. So you can almost think like a header tube coming out, a flexible hose that wouldn't affect flow, so big enough where it won't make a difference. And then the bolt to here. Then I needed one from the intake port to go to this bench. So some adapter to the end of the intake port that comes out and goes to this bench, and then measure it. Because during this overlap time, remember the valves are only open maybe 1 or 200 thousandths. So we're talking like a max flow of maybe 250 CFM on the intake and maybe 130 on the exhaust. So not a ton, so it should have been easy to accomplish. Of course, I don't have the stuff to make the CNC things to make that happen, but I sure wanted to test it. Anyway, that's something I just want to show with you guys, because it could give away, it could tell me how I could have changed my ports maybe to help with crossflow. They would help it capture more during the overlap and kind of change things. It would also give me more information to give to a cam designer, be like, hey man, I remember I don't design cams, but I sure do spec them. But it'd be easier to be like, I know exactly now how much of this thing moves. I could change things around with my open and closing points. I can adjust it. I know what it's going to do here. Got it. Anyway, just more information. Anyway, guys, thanks for watching. This is a long video. I'm probably going to splice it up and use it in different ones again. And I hope I gave you something to chew on. And I hope you didn't lose you in the first 4 minutes or whatever. And I talked about the problems I have in the shop. But hopefully I gave you something good. But I promise to answer your questions, and I hope I did. You guys, take care.